This is a demo of how to do self-organizing maps and their variations as well as LVQ inside Neuralworks. So the first thing we're going to do is solve the iris problem using a self-organizing map. So you can go to Instanet, down to self-organizing map, click on that. And you get the normal dialog box where you tell it how many inputs there are. This is the iris problem, so there's the 4 values that are the measurements of the petals and sepals. This is a grid of cluster neurons or exemplars or cluster units that we're going to use. Right now we don't have any outputs, so we're going to leave that as 0. This is a pure self-organizing map with cluster units. Don't need a coordinate layer or an output network or a min-max table or interpolate, although we can leave those checked. We don't need connect prior, connect bias. This is irrelevant right now, but let's choose delta rule and sigmoid because we'll need that in a bit. And let's grab the iris training and testing files. We can set epoch from file, although the epoch doesn't matter right now. So this is going to generate a 4x4 grid of Cahonin self-organizing neurons that are going to cluster the data coming in from the iris. So we'll say OK here. We want to choose both frequency estimates and SOM weights as output maps. And we can save those selections. So we're going to get 2 things I'm going to make bigger here so we can see the progress of how this thing works. Alright, so here, down here is our network. And here's our 4 inputs down at the bottom. And then this is a grid of 4x4 Cahonin self-organizing map cluster unit neurons. So our network's set up. To run this, you got to run, say learn, and this thing runs until, or learns until. So this is, remember there was the stopping condition, so that's what it's going to do. We'll click OK, and it runs. And over here, the SOM weights are the values of the exemplars. So remember this has 4 inputs, so each exemplar has 4 elements in its vector. So 1, 2, 3, 4, that's the first exemplar. 1, 2, 3, 4 up here is the second one. 1, 2, 3, 4 is the third one, and there's the 4th one. So by looking at these, you can see that the data got grouped in kind of a category down here, something in the middle that looks different, and then way over here you've got these that have the big long, big empty squares. And these are proportional. The size and the filling is proportional to the value of the data that's stored in that exemplar vector. This shows you how many data points came in and were stored in each of these exemplars in the 4x4 grid. So there were a lot here, not so many here and here. Alright, so that's the SOM, self-organizing map. We just did that. Let's say we make the self-organizing map bigger. So instead of a 4x4 grid, we can go to a 10x10 grid, which may help it cluster better. Again, we're not going to do any learning. This is just self-organizing. Same data set. Close the existing network. Keep those. Let me rearrange these. Alright, notice down here we've got a bigger grid, and it's suppressed the connections because there's so many. We still have the 4 outputs down here, 4 inputs down here at the bottom, and 10x10, so there's 100 cluster exemplar neurons, self-organizing map Cahonin neurons. Do the run, learn, until, say OK, and here it's even more clear how there's 3 groupings. There's a cluster here, or a grouping of like input values, another grouping in here, and then another one down here. So there's definitely 3 categories of data in the iris data. At no point did we tell the network that. We simply fed it the input vectors, and it figured out there were a whole bunch that were alike here, a whole bunch that were alike here, and then some in the middle. All right, so that's the 10 by 10. The disadvantage here is we have no idea which data points, which records from the input data set, the iris data set, ended up where. Is this the fourth one, the fifth one? What's being clustered together where? So we can add another element here. So we're still going to do the 10 by 10, and then we're going to click coordinate layer. So what that does is it tells the XY coordinate of each record that comes in to the self-organizing map from the input files. So all we've done is click coordinate layer. Everything else stays the same. We're still not doing any learning. So we're going to say OK, close the network, use those. Again, we'll spread these out so we can look at them because they're fun to look at. Here's our network 10 by 10. Here's our 4 inputs, but notice that there's an extra layer here now called the coordinate layer. This is X and Y values of where each input data gets clustered. So say input record number 20 comes in, and maybe it gets clustered in XY coordinate right here. So let's go ahead and train this again. We'll learn, run until we get clustered. And now we're going to test on the testing data. So we're going to do run and test. We're going to say one pass all because that's what we do when we test. And this creates an NNR file just like normal inside the directory where the current directory of the program is located. I'm using the install directory. That's just the easiest way to do it if I'm on my local computer. So I've got a file here called iristest.nnr. It was just created. And I'm going to open this with Notepad. And notice it's already associated this type file with Notepad because I've done this before. And so what I have in here, for each input record in the testing data set, I get a set of XY coordinates. So it says that the first record that came in got clustered at an X value of 0.94 and a Y value of 0.981, or sorry, 0.3819. Again, what does this mean? Well, let's go into Excel and grab this data and import it into Excel. So I'm going to go edit, select all, so I'm just grabbing all of the data inside here. Then I'm going to copy it. I'm done with Notepad. Going to open up an Excel book here, new worksheet, and I'm just going to right click here on this cell A1, and I'm going to paste the data in, and it gives me a blank column here which I don't need, so I'm going to delete that. So here's my XY coordinates. So I could do an XY plot, but what am I going to plot? I want to see, well, how well did it cluster the data? And we happen to know that the way that the data is in the testing data set is that it's the first one is the Setosa, the second one is versicolor, and the last one is virginica. So I'm going to assign the numbers 1, 2, and 3 to each of those categories, and then do a bubble plot just to see whether it really did cluster the different species in different locations. So I need to copy this multiple times here. Again, I can only do this because I know what the clusters, the target clusters should be, but we're just going to check to see what Neuralworks did with this self-organizing map. So all of the 1s should be Setosa, 2 should be virginica, 3 should be versicolor. Now I'm going to do a bubble plot. So I'm going to highlight these 3 columns. I'm going to go up here and do an insert, and in charts, and I just realized I have to remember where this is. Bubble chart is right here. So I'm going to do a bubble chart like this. And what that does is it creates a bubble whose size is the number in that C column. So each bubble here is located at the X, Y coordinate, and then a bubble of size 1 is plotted here, and then at this coordinate here, a bubble of size 2 is plotted here. And if you look at this, you can see, let me make it bigger. You can see that the big bubbles are down here, the medium bubbles are here, and the smaller bubbles are here. So the Setosa all ended up grouped here, the Virginica in the middle, and the versicolor here. So it really does group, and it grouped it without knowing what the correct answers were. We simply used the correct answers to see, well, how well did it do the grouping. All right, so that's our Excel of the SOM. All right, so there's one more thing we can do with this that's useful. Remember when we talked about counter propagation, we talked about how we could add a backprop layer on top of the Cahonin network, our self-organizing map. So we can do that inside Neuralworks. We can choose self-organizing map, use the 10 by 10 grid. We still have the 4 inputs, but now we can say, okay, there's going to be an output layer of 3 categories, and we're going to add that output network. So you have to check this box. You have to check the 3 here. And then what that means is that the Cahonin map is done from the inputs to this 10 by 10 grid, and then the 10 by 10 grid connects to the 3 output neurons with back propagation weights that are trained with backprop. So now we choose the delta rule and the sigmoid. The min-max table becomes important because we're doing backprop. Still have the same data sets. Set epoch from file here. And we want a bias neuron here as well for that backprop layer. So now we're going to create a new network. Close this one. RMS error, and we can still do the SOM weights and the frequency estimates if we want. Took me a little while to grab that. And here's my RMS error. So let's drag that all the way across here. Move this down here. So we can see all this. And now let's look at the network down here. Notice that there's an output layer. 3. So there's the 3 values 0, 1, 0 that's going to be associated with the categories. Here's the Cahonin layer, and I accidentally dragged off the bottom, the input layer, but you guys, it's the same as what it's been before. So now the inputs are connected to this 10 by 10 grid as exemplars, as the Cahonin layer, and then the one that classifies in here that grabs onto the input then sends a 1 out through weighted connections to the output layer, and we train that with backprop. So let's go run, learn, and this is going to tell it to learn for that many training passes, so there's no until anymore because we're doing backprop as well. And notice we get the SOM happening, the frequency estimates happening, and we get training here with this backprop network. We can train some more. And keep doing this. Notice that we don't get really great error. In fact, we did a better job classifying here with the just straight backprop network. And that's because sometimes adding an SOM layer is a really good thing, and other times it just doesn't help at all. But you can use this self-organizing map to figure out clusters and then do a backprop layer to recognize, well, what do you have when you're all done with the self-organizing map. All right, the last thing I'll show you here is the LVQ network. So this is InstaNet Learning Vector Quantization. Remember, this is that self-organizing map, and it's going to have a backprop layer on top of it, And it's doing the plus minus learning that we talked about during the last lecture. So we can do an LVQ network. We're still doing the iris data set here. And this tells it how many Cahonin neurons to use. We're going to change that to 7 because I've played around with this before. And we're going to change this to 2250. I'll get that typed right. So here's the inputs. There's 4 inputs. There's 7 Cahonin neurons. And then there's 3 outputs. So it's doing the whole thing all at once to essentially do LVQ and backprop all on top of each other. Notice min-max table. So we're going to go ahead and say, okay, let's create this network. Remember the LVQ network, it had groups of clusters. So we've told it, okay, there's a cluster 1, cluster 2, cluster 3, because now we're doing supervised learning, and it read in that iris data set and said, okay, there's 3 categories set up with this. There's 4 inputs, 3 different categories. Each category has 3 cluster neurons inside it, and then it's going to backprop recognize to the different categories or the different classes here. Let's do a run, a learn, until. Notice it learned down to 0 error. Not bad. And that was very quick. And then we can do a test. And we get about our normal error because remember there's measurement error inside this data set. The key feature is that the training happened very quickly and it trained to 0 error. Looks like I have to recreate the network. So we did get 0 error that first time we trained it. So that's the end of this lecture, how to do an SOM, how to do an SOM with a coordinate layer so you can figure out what's going where, and then add a backprop layer on top of that to do counterpropagation. And then another tool is this LVQ network that combines backprop and SOM as well.